Hi guys, so this is the last section, chapter 4, section 4.4. So what we're looking at is evaluating the linear model. So we're going to look at use linear models to describe associations only when appropriate, and then also compute and interpret the coefficient of determination. Right, so looking at slide 2, there are some cautionary notes regarding regression. So let's go over those. So the first one is don't use linear models to describe nonlinear associations. Always look at a scatter plot first, right? So this is cautioning us that it doesn't make sense to make a linear model or find R, right, the correlation of coefficient. It doesn't make sense to find those find those items if our data doesn't look to be linear, right? So always start with the scatter plot, right? That's the biggest thing that you got to make sure to do. Um, Next thing, another big item is that just because two things are correlated doesn't mean that there's causation, right? So here it says an association between two variables is not sufficient evidence to conclude that a cause and effect relationship exists between the variables, right? So two things might look like they have an association between the two that's linear, but again, it doesn't mean that if one thing happens, another thing is guaranteed to happen, right? That's not guaranteed, right? So you want to be careful with that when you interpret things, right? Another item is you want to be aware of outliers. So sometimes an outlier can have a big effect on R. So again, you always want to check the scatter plot first, right? So if you exclude one point from your data, it could drastically change your line of best fit, right? In fact, there are some examples in the text, right? So I can't pull this up for you on the screen because Pearson is currently down. Let's see, 4.4. Right, so this is talked a lot about on page 171 in your text, right? So you can take a look at that. But it talks about what we call influential points, right? So a point is influential because their presence or absence has a big effect on conclusions, right? So there's figure 4.28 so figure 4.28 on page 171 gives a good example, right? So you're looking at population density versus crime per 100,000 people in 2008, and there's one big outlier, which is what Washington D.C. So there's one item on the left that includes Washington D.C., and then on the right they exclude it, and it just makes a big difference, right? Your R value goes from 0.412 to negative 0.145, and and the slope of the regression line goes from positive to negative, right? So it makes a big difference. So so when you're looking at the scatter plot, you want to look for outliers and also if there exists a linear relationship or not. And then lastly, a big item is don't extrapolate, right? So I went over in the last video talking about extrapolation and interpolation. So remember, extrapolation is where you are so extrapolation is where you're going outside of your data set, right? So you're either below your data or bigger than what your data values are. And interpolation is where you're in between data values, right? So extrapolation can be very dangerous. You can get unrealistic results, and we really don't know what happens before or after our data, right? We're given just this very narrow snapshot. So it's very possible that the data could be nonlinear, given our narrow focus. Right. All right. So let's go to slide 3. All right. So slide 3. So I don't think I put this in the PowerPoint I put on Canvas, but I just pulled this from section 4.3 and just slid it in here, just to refresh us of the data set, right? So if you remember, we looked at this data set between height and weight for 6 women, right? And we made a regression line and so forth. So if I go to the next slide, this is the slide that you have. So it's just saying, in a previous example, we found there was a strong linear relationship between heights and weights in women, and the regression equation is weight equals negative 442.882 plus 9 and 3/100 times height. So it says, what weight does this equation predict for a woman who is 36 inches tall, right? So if I go back to my data, so for height, the lowest height I have is 61 inches, and this is asking you to pick 36. So this is extrapolation, right? We're before our data set. We can't go, so if I go back, right? So anything below 61, right? So like 60.5, 60.99 would be considered extrapolation, right? And anything above 68 would be considered extrapolation. So you don't want to go below or above your min and max of your x-axis, right? So let's go to the next slide. So the next slide, we have it calculated. So we get weight equals negative 117.8 pounds, right, when we plug that into the equation. And again, this gives us an unrealistic result, right? Someone can't be negative pounds. So that's just one thing to be cautious of, right? So it's recommended that you don't extrapolate, right? So then another big idea in this chapter or this section is looking at the coefficient of determination, right? So we looked at the coefficient of correlation, right? Just R. So if we take R and square it, we get what's called the coefficient of determination. So usually we take this value and we can convert it to a percentage, so it's always between 0 and 100%, right? And if it's in decimal form, R squared is always going to be in between 0 and 1, right? So what R squared does is it measures how much variation in the response variable is explained by the explanatory variable, right? So it helps us explain the variation, how much is explained by our model. So another note here, the larger the R squared value, the smaller the amount of variation or scatter about the regression line. Right, so larger R squared values are good, right? So here's an example. So this is using the data on the car age and predicted value that we looked at. So earlier we got an R value, correlation coefficient of negative 0.778, which is a fairly moderate negative correlation, right? Linear correlation. So it says compute and interpret R squared. So to find R squared, we simply just take R and square it, right? So after doing so, we get 0.605, right? Or we can also represent that as a percent, right? So to write that as a percent, you would multiply times 100%, so that moves the decimal spot over twice, so we get 60.5%. And how we can interpret this is that car age, right, or x value, explains about 60.5% of the variation in the car value, right? So it lets us know how much of the variation does our x value explain that's in the y value. Right? So that's the end of that slide. What I would like to do now is I want to take this data and show you how to find r squared in the calculator and then also in R, right? So let me pull up the graphing calculator and we're going to enter in this data. Right? So to do this, we need to turn the calculator on, and then you're going to go into the stat menu, right? And we go to edit, right? So we just need to input the data first. So I'm going to put the height in L1. So we got 61, 62, 63, 64, 66, and 68. Right, and I'm going to go over here and enter in the y values. So I got 104, 110, 141, 125, 170, 160. Right, so I got my data entered in. I'm going to go to second quit, right, just to get back to the blank screen. You don't have to do that, but I prefer to do that. So then now I'd like to hit stat menu and then go over to calculate. And we need to go over to option 8, right? Calculate the linear regression line. So L1 is X, L2 is Y, that's good. So then go down to calculate, hit enter, and I'm not getting my R value, right? So I did this on my other computer, right? So remember I told you if it's not showing up, what you have to do is go to second catalog, and then we're scrolling down to, I believe it's called diagnostics. So go to the D's. And you only have to do this once, right? So we want diagnostics on, right? So I'm going to hit enter beside that and hit enter again. So now it's on. So if I go back to stat, calc, then it's option 8. Then go down to calculate. There, so now I'm getting r squared and r values, right? So you can see there's my r and there's my r squared. So with this model, 77.6% of the variation in weight is explained by height, right? So that's how you can find the r squared value and then also interpret it, right? So now let's do this in R. Alright. So actually I'm going to go split screen with R and my graphing calculator, because I can just get the data from my graphing calculator since I already typed it in, and that'll take up less room so we can see more of R, right? So I'm going to make my font bigger. So that's something you might want to do. I mean, even if I'm not making a video, if I'm just using R, I always make the font larger. So that's up to you. Alright, so let me pull up my data. So I don't need to worry about working directory. We only have 6 numbers to type in for L1 and L2, so I'm just gonna type it in by hand using the C command, right? So I can do X equals, and then I can do C C command, then just type in my numbers. So I have 61, 62, 63, 64, 66, 68, right? So 1, 2, 3, 4, 5, 6. Yep, I believe I have them all. And then I'm just going to type y equals and then do the C command. So 104, 110, 141, 125, 170, 160. right? So then now I can use the correlation command of x and y, right, to find the correlation, and then I can, so to find r squared, right, we're just going to square it, so we can just type in the command inside of parentheses, right, and then hit the exponent button, so shift 6, and then hit 2 and hit enter, and there's my r squared value, right? So let me fix that so you can see it better, right? And if we compare, so go to stat calc option 8 and then calculate, right? So you can see that matches exactly, right? So my calculator just had more decimal spots, right? All right, so that's how you can find that using your calculator or R, right? So you definitely want to know how to find it with the graphing calculator. You're going to have to do that for the exam, right? But remember, for the R assignments, I'm going to test some of your skills. Can you use the statistical software, right? Because again, just to reiterate, typically we would have many values, not just 6 values here. Maybe 150. I don't want to type 150 numbers. Well, it'd be 300, right? We'd have 150 for x and 150 for y. I would not want to type in 300 values in my calculator, right? I don't even want to type in 50, right? That's a lot to type in. So that's where R is a lot better, right? But the graphing calculator works great for things also. All right, so actually, I think I just thought of a way I can bring up some materials I was wanting to pull up. So I'm gonna pause this. I'll be right back after I find it. All right, so I uploaded this. Am I recording? Yep, good. All right, so I uploaded this resource into Canvas. So this is from a different textbook, but I really like how they explain extrapolation in this text. I really like the textbook that I picked for this class. I think it's a great read, but I do think one thing they could do a little better on is explaining extrapolation. So I want to walk through this. This is a example that I think is really good. So here it says the U.S. Census Bureau reports the median age at first marriage for men and women. So here's a regression of median age at first marriage for men against year since 1890 at every census from 1890 to 1940, right? So we're given R squared value, so 92.6% of the variation is explained, right, by the model. So that's good. And then we're given the intercept, right, and the coefficient for the year, right? So that's the slope, right? So here's the regression equation that's provided. So we have the average age equals 25.7 minus 0.04 times year, our variable year. So then now it says, what would this, so let me zoom in a little bit. So now it says, what would this model predict as the first age at first marriage for men in the year 2000, right? So when year counts from 0 in 1890, the year 2000 is 110, right? So substituting 110 for year, we find that the model predicts a first marriage age of, we get 21.3 years old, right, after plugging it in. So in the year 2010, the median age at first marriage for men was 28.2 years. What's gone wrong, right? So when we look at our data set, right? So these blue dots represent, this is the data that we have, right, between the years 1890 to 1940. Now, the problem is that's the only data that we have. So going out before or after that range is extrapolation. So what we have now is we added more years in, right? So we have green, we have the red, but what happens? It's not linear, right? Now that I have a bigger picture, you can see that this doesn't become linear. Now it's more of like a parabola type shape, right? So that's why extrapolation is dangerous, right? So if we only have the blue dots, that looks to have a strong linear relationship. But by going outside the data range, we don't have we can't tell the future. We're not quite sure of what the data does after the year 1940. So it could keep going on in a straight line, but here you can see it doesn't, right? So this is a resource, again, I uploaded on Canvas that I'd recommend reading through, but hopefully talking through that helps a lot, right? Um, so you can find that useful. All right, so that's the remaining part that I have from chapter 4, right? So again, one of the biggest things you want to remember is when we're trying to do some regression, some linear regression, first thing you want to do is look at the scatter plot, right? Look for outliers, look to see if our data looks linear, right? So that's before you do anything else, right? All right, well, that's all I have. I'll see you guys in the next video.